Welcome to the second Innovation Builders webinar. Thank you for joining us today. My name is Sabrina Devone, and I will be the moderator for our presentation. I am a member of our Business Transformation and Innovation group within Fluor. This technical presentation highlights the value of accurate thermodynamic modeling on process design and safe and trouble-free operation. As safety is one of our core values at Fluor, we will start with a safety topic about the importance of knowing flammability limits. The fire tetrahedron has replaced the fire triangle to understand the ingredients necessary for most fires. A fire requires an ignition source, oxidizer, flammable material, and a chain reaction to sustain the oxidation. The concept of flammability limit is important to understand because fires will not start if the fuel concentration is outside the flammability region. Our speaker, Paul Mathias, will talk more about flammability limits in his presentation shortly. Paul Mathias is a chemical engineer with over 41 years of broad experience and an expert in applied thermodynamics and process modeling. He started his career on the Aspen project at MIT, which developed the forerunner to Aspen Plus. He worked at Aspen Technologies before joining Fluor in 2005, and Paul has chaired sessions at the American Institute of Chemical Engineers and other technical meetings, and was selected as an AICHE Fellow in 2015. Paul is also a Fluor Senior Fellow and has 6 patents, over 90 publications, and has given over 130 technical presentations. Before we get to the presentation, a couple of housekeeping items. The audio lines for participants have been muted to eliminate background noise. The session today is being recorded and will be stored in the United States. Please make use of the Q&A tab to ask any questions, which should be addressed to all panelists. And we will pause several times to address questions that come through the Q&A. So with that, it is my pleasure to present Paul Mathias. Paul.
Thank you, Sabrina. I'd like to add my own welcome to all the attendees at this webinar. I hope you find the webinar to be interesting and useful. The perspective paper that Chao Chen and I published in the AICHE journal offers a good way to provide the motivation for this webinar. About 18 years ago, when we both worked for Aspen Technology, Chao Chen and I published our perspective on applied thermodynamics for process modeling. Chao Chen is now a professor at Texas Tech University. The process industry spends a lot of money, in fact over $500 billion US, to design, build, maintain, improve, and troubleshoot chemical plants. Process modeling has become an essential tool to execute these efforts, and in turn, process modeling is enabled by models that capture the thermodynamic properties and phase behavior of the various chemical compounds in the process, whether they are feedstocks, products, undesired impurities, or unwanted side products. Applied thermodynamics is widely and clearly recognized for its contributions to process technology. A less appreciated value is its contribution to safe and trouble-free process operation. This underappreciated value is the focus of today's presentation. In today's webinar, we will present 3 case studies to highlight the role of applied thermodynamics in achieving safe and trouble-free process operation. In the conclusion section of our 2002 perspective, Chao Chen and I wrote that applied thermodynamics will continue to provide value to chemical engineering by focusing on the needs of practicing engineers. We chose these 3 examples as we feel they will be of interest to practicing engineers. Let's now move on to the first case, which is the study of mixture flammability. Fluor received this query from a client to evaluate the flammability risk of a fairly large lab reactor developed for the purposes of desulfurization research. Although it is a lab reactor, it is quite large. 100 gallons is about 7 times the average fuel tank capacity of an automobile. The liquid the client told us was kerosene. And when we asked what kerosene, they said, well, it's kerosene. And so that pointed out to us that we needed to be conservative. The temperature in the reactor is 70 to 80 Celsius, and the desulfurization agent is hydrogen peroxide, which causes elevated oxygen levels in the headspace. This could be 27 to 28 mole percent, but possibly as high as 30 to 60 mole percent. And the vessel was closed when we started this study. So we had two questions before us. One is this vessel a flammability risk? And the second one is, if it is, what design changes should be made? Flammability is a complex subject and has many definitions and technical terms. Here we focus on just two important properties, the flash point and the low flammability limit. The flash point is the lowest temperature at which vapors of a volatile material will ignite when given an ignition source. The low flammability limit defines concentration. So it is the lowest concentration of the gas or vapor capable of producing a flash of fire or explosion in the presence of the ignition source at a given temperature and pressure. And this was the concept that Sabrina introduced to us. The approach taken in this study was to estimate the LFL and then make sure it is lower, much lower actually, 4 times or 5 times lower than the concentration of flammable kerosene components in the headspace of the reactor. Well, how do we estimate the flash point and LFL? This particular slide defines how we estimate the flash point. Our guiding principle in estimation is to use data as much as possible. So here we describe kerosene as a mixture of N-alkanes, known compounds, and we got the flash points from the DIPPER database. So that means that those flash points for the pure components are accurate. So we now need to move to the estimation of the mixture flash point temperature. This equation actually has a long history. It was proposed by Le Chatelier in 1891, almost 130 years ago. The numerator is PI, or the partial pressures, and those are calculated by doing a vapor-liquid equilibrium or a flash calculation. That's an independent calculation, but for kerosene, that should be rather simple. Yeah. The denominator is the vapor pressure of the pure component at its flash point temperature. So you can see that this equation is reasonable if you look at the pure component limit, because the PI would be equal to the vapor pressure, the denominator is the vapor pressure. So if we apply the temperature of the flash point, we get 1, and the equation is satisfied. This equation has actually been evaluated in lots of publications, and it turns out to be quite accurate. So in summary, the estimations are estimated to be accurate if 1, the flash point of the pure components are known, and we know that they're known. And the second one is the phase equilibrium can be reliably calculated. Let's now move on to the estimation of the effect of temperature and oxygen levels. The two publications here in the box at the bottom actually define where we got our information from. Let's start with the temperature. LFL TFP is what we calculated in the previous slide, and LFL-T is the flash point at some different temperature, typically a higher temperature. So you can see the equation here defines how the LFL decreases with temperature. And I want to let you know that this is a relatively small correction, but as I'll show you later, The effect of temperature actually shows up because it sharply increases the concentration of the kerosene components in the headspace of the reactor. The second thing we need to estimate is what does the oxygen level do? Somewhat surprisingly, it turns out that the oxygen level, higher oxygen levels do not considerably decrease the LFL concentration. And so we assume that there is no effect. Now that we have our estimation procedures done, the next thing is what is the composition of the kerosene? And that's defined in this next slide. As I mentioned to you before, there is a need to be conservative because we didn't know exactly what kerosene our client was using. So we come up with two of them. Kerosene 1 is a higher boiling, and you can see that it's got a higher flash point temperature, about 73 Celsius. Kerosene 2 is another valid kerosene, but it's lower boiling points. You can see it starts to boil at about 100 Celsius and is completely boiled by something over 200 Celsius. And you can see that that makes a considerable difference in the flash point temperature as it drops from 73 to 31 Celsius. Kerosene 2 is just something we thought would go in the middle. So now that we have our kerosenes, we still do need to evaluate how well the model works. In particular, we want to evaluate how well the model captures the composition dependence of the kerosene. In the next slide, we showed these effects. As you probably know, it is absolutely vital to validate all models used. The first chart on the left shows the effect of adding N-pentane to our kerosene 3 shown on the previous slide. Generally, we expect that as you add a lighter component, the flash point temperature would go down. And so you see that if you add about 2 mole% pentane to kerosene, the flash point temperature decreases by about 30 Celsius. The important point, though, that I want to leave you with is our estimation procedure captures this effect very well. On the right, we show another example, and this is where nonane, again, a lighter component, is added to tetradecane. And again, you see even half a mole% could drop the flash point by a good 60 Celsius. And again, the model captures. So I want to leave you with the message, though, that's something that we do, and probably you do too, is that you must validate models used. We are thus confident that we can accurately and reliably estimate the flash points and the low flammability limit of the kerosene sample. We can then go on to do the calculations and provide a results table to our client. Let me go to the end first, and then I explain the chart. What we need to do is to calculate the lower flammability limit and also the actual concentration coming from a flash calculation at the temperatures of interest, which here are 70 and 80 Celsius. And that ratio determines whether the reactor is safe or unsafe. Typically, for a safe reactor, we would expect that ratio to be less than 0.25. And you can see here that none of them are less than 0.25. But with that, let me just explain some of the details. We have kerosene 1, 2, and 3. And as I've showed you before, their flash point temperatures vary from 31 Celsius to 73 Celsius. From our flash calculation, we can calculate the mole% of these kerosene components in the headspace. And then, we can calculate the lower flammability limit at the flash point temperature, pardon me. And then we apply the temperature correction to say what is the flash point at the temperatures of interest. And you can see it doesn't vary by a whole lot. For example, for kerosene 2, it goes from 0.81 to 0.75 when we raise the temperature to 31 to 80 Celsius. More importantly, though, the actual concentrations could go up considerably. So if we look at kerosene 2, the concentration goes up by a lot as we raise the temperature from 31 to 70 or 80. And that gives us this enormous ratio of 7.5 or almost 12 as the ratio. You'll recall that I pointed out that this ratio should be less than 0.25 for a safe reactor. So then it's clear what recommendations we could give to our client. One is this vessel should not be closed. And secondly, a purge system should be designed such that the hydrocarbon concentration in the vapor space is less than 0.25. So this concludes the first case study. Sabrina, I think we can go to the chat and see whether we have any questions.
Thanks, Paul. Yes, we will pause for a question or two. And so if you have a question, please type it in the Q&A section and be sure to address it to all panelists. So our first question, Paul, is what is the DIPPER database?
Well, that's a good question. The DIPPER database comes from AICHE, and going back about 40 years ago, AICHE formed a consortium to provide data needed for the chemical process industries. And DIPPER stands for Design Institute for Physical Property Research. You can go to the AICHE website for more information. But let's tell you one thing, and that is the biggest product, probably the most popular product from DIPPER, is the Pure Component Database. They call it Project 801, which started in 1980, and it was the first project. You probably have used DIPPER, maybe if you don't know it, because it's like Intel Inside, because all the commercial process simulators actually use the DIPPER database. You can also get the most recent versions if you're a member of the consortium. And if your company is not a member, I recommend that you look into it. You can contact me for details. Thanks for that question, Sabrina.
Thanks, Paul. We have another question. Will there be ignition if we are above the LFL level without ignition source?
There will not be ignition above the LFL level. Sorry, pardon me. You asked whether there will be ignition if we're above the LFL.
Yes.
The simple answer to that is no, but the safe answer to that is we should be very cautious, because we've seen, for example, I live in California, and we've seen the devastating fires that were caused by electrical equipment flashing. So you never know where the flash is coming from, or how small a flash would be needed. So you've got to be safe. I think if you're doing process, if you have process equipment or process designs, we recommend that you stay below 0.25 of the low flammability limit.
All right, thank you, Paul. We will pause questions for now and move on to the second case study. We will have 2 more opportunities to respond to questions during the presentation, so please continue to send your questions. Paul?
Okay, thank you, Sabrina. Let's move on to the second one, which is aqueous dew points. Aqueous dew points are typically quite easy to estimate. For example, rain occurs when the relative humidity, which is actually defined as the mole fraction of water times the atmospheric pressure, and divided by the vapor pressure of water at the temperature of it. If that exceeds unity, then typically we'll get rain. And so that's a relatively easy thing to calculate. However, aqueous dew points are much more complicated in chemical process plants, because the vapor phase may contain contaminants, and in particular the contaminants that are bad are acid and base contaminants. And this is the subject of the second case study. This case study refers to corrosion problems in a thermal cracker product that was brought to us by a client. One of our clients reported aqueous phase corrosion at a temperature above the water dew point. But this, of course, immediately raises the question as to what is the water dew point, and that's going to be the subject of this case study. But let me first give you the background details. The composition of the thermal cracker non-aqueous components goes from about methane as a very low boiling point to about hexane, and these solid dots define the so-called known components. Traditionally, we have described the higher boiling components, and there could be many of them, as so-called pseudo-components that are defined by their boiling point. And you can see that the boiling points here go from something of the order of 95 Celsius to something close to 300 Celsius. The other point is that this system contains water. In this case, it's 5.5% water. And the acidic impurity that I alluded to earlier is sulfuric acid. And here the concentration that we were told of sulfuric acid is 5 ppmW, or 5 parts per million by weight. So the questions we studied were, what is the water dew point and how does it vary with the sulfuric acid impurity level? And that will be the next slide. This is a rather complicated system, but fortunately we have a reliable model for systems containing hydrocarbons and sulfuric acid. We did lots and lots of calculations to understand the phase behavior of the systems. And one point that I'd like to make to you, which you probably understand as well too, is that a good model, a good thermodynamic model, can serve very nicely as a virtual laboratory. So here are the results from our virtual laboratory. This graph has two y-axes. Let me start with the y-axis on the right. This one shows the water mole fraction in the vapor phase, Y water. And it's got a funny looking shape, right? It's an inverted V with an apex of about 120 Celsius. So the question is this correct? Well, we did a lot of analysis and we concluded that it is indeed correct. And the explanation is actually quite simple. Imagine we are at 200 Celsius, right? There is no water vapor phase. There is a hydrocarbon vapor phase and a hydrocarbon liquid phase. As you drop the temperature below 200, some of the hydrocarbon components will condense. But the water essentially will not condense because it's got nowhere to go. The solubility of water in hydrocarbons is very low, and for all practical purposes can almost be thought to be zero. When you get to 120 though, a water phase starts to form, and now you can see that the water concentration in the vapor phase drops quite sharply, and at ambient temperatures at 20-30 Celsius, it's almost zero. So we asked the question then, so 120 is the water dew point? And the answer is, well, almost, but not quite, because it really depends on the small concentration of the sulfuric acid in the system. So let's now move to the curve on the left, which is showing the weight percent of the aqueous phase. This is the total amount of aqueous phase divided by the total of everything as a percent. So you can see at low temperatures, when all the water is in the liquid, it starts off at about 5 weight percent, which, as I've told you before, is the total amount of water in the system. I want to point out to you that this y-axis is on a log scale and goes through about 6 orders of magnitude, and that point becomes important later. So now as you drop the temperature, you see that the total amount of the aqueous phase drops, but only gently, very little bit, until you get into the vicinity of 120, then it starts to drop very sharply. And if indeed there was no sulfuric acid in the system, the dew point would be 120 Celsius. But now think about what happens when you actually have sulfuric acid. Sulfuric acid is not volatile at all. So as you get down to 120 and most of the water evaporates, now you're left with a very concentrated sulfuric acid. And so we get this funny looking shoulder or shell, and that could go quite a bit. So you can see if we have our base case, which is 5 weight percent, the dew point can be raised from 120 to about 180, which would be a dew point elevation of 60 degrees Celsius. We also did other sensitivity studies to say, for example, well, what happens if we raise the the sulfuric acid concentration 5-fold? And you can see it increases, but not by a whole lot. We next ask the question is what happens if we decrease it? And the green line shows what happens if we drop it by a factor of 10 from 5 ppmw to 0.5 ppmw. And again, the effect is relatively small. And so this tells us that a little bit of sulfuric acid can cause a lot of problems. It can raise the dew point by a lot. And if you don't have the right metallurgy at the higher temperatures, the corrosion could do a lot of damage. Let me just show you another example to sort of reinforce what I'm saying here. The right-hand axis is exactly the same as before. The left-hand axis shows now the pH of the aqueous phase. If you go to low temperatures, say again 20 Celsius or 30 Celsius, you can see that increased concentrations of acid will decrease the pH. And of course, this is an expected effect. So the pH could go from something like 3.5 to 0.5 ppm sulfuric acid to about 2 to 25 ppm sulfuric acid. Well, what happens as we increase the temperature, and this is similar to, but not exactly the same as the previous chart. As you get to where all the water is mostly evaporating, all these curves kind of coalesce because it's the sulfuric acid gets to the same concentration, and actually temperature determines its vapor liquid equilibrium. So what we want to see here is that this chart actually reinforces the previous chart and gives us confidence that the calculation is actually good. Let me then move to a summary chart just to show you the main effect. So again, I've dropped out the right-hand axis because really what we need to focus on is this fact, and that is 5 ppm of sulfuric acid can give you a dew point elevation that's very much. I should point out that there's not a lot of the liquid phase here. You see that when we get the shell starts, it's about 10 to the minus 3, which is 0.001 weight percent, which actually is about 10 ppm by weight. Not a lot, but certainly enough to cause damage. So the message I'd like to leave you with is that small amounts of sulfuric acid or another strong acid can create a great deal of problems. Let me then go down to summarize what I've told you about. The first one is, as I've emphasized before, and I will continue to emphasize, the validity and accuracy of the model is something we as practicing engineers must really pay attention to. Calculations have good trends and therefore are expected to at least be qualitatively accurate. We know that the water dew point without acid is good because it mainly just depends on the vapor pressure of water, which we know very well. The pH calculations reinforce the VLLE or vapor liquid equilibrium calculations and also provide an indicator of the sulfuric acid concentration. Lastly, what is the uncertainty? As a very conservative estimate, we feel that the calculation, the elevation is good to say 10 to 25. That's probably overly conservative because our model for sulfuric acid is good. That then gets us to the problem mitigation. And the first one is to be cautious. Like I replied to the previous question that came from the chat, will we get a fire when we are within the flammability region if there's no spark? I don't know. But let's be cautious. Let's have sufficient temperature margin. Second mitigation step possibly is to reduce the organic oxygen that causes the formation of H2SO4 from sulfur compounds. But again, I want to caution you that even very, very low levels of sulfuric acid cause a considerable increase in dew point. So probably we are left, I'm going to give this double tick marks, because we really do need to be cautious and put in a safety factor, which would be a good temperature margin. I want to give you one related example next, just to show you that this is not really an isolated example. I'm going to show you here the dew point elevation when we have a slightly different system. In this case, we have HCl, which is a strong acid, and ammonia, which is a weak base. And as you probably know, when you have the two together, you have very strong interaction between them. So let's look at our chart. We have a chart similar to the ones I showed you for sulfuric acid and water. And the dashed line would almost be analogous to the previous one. This one has a higher concentration of water. So you see the water dew point is something of the order of 190 Celsius. And then we get the elevation, we almost get a 90 degrees Celsius increase in the dew point. But one of the interesting twists to this system is the possibility of solid formation. So let me show you that next. When we take a lower concentration of water, we get a water dew point, which is about 120, and then we get a liquid dew point of something like 200. Note that this elevation is considerable, but the interesting twist we get here is that at higher temperatures, we still get some precipitation, but it would be solid precipitation given by the dotted line. And here we get the formation of ammonium chloride solid. The curve on the right kind of shows how these two different curves come about. The red line is the solubility of ammonium chloride in water. And you can see it's quite a bit. It goes from about 20 weight percent at ambient temperature to something rather high, very, very high, but as the temperatures exceed about 200 Celsius. So let's look at the concentration of ammonium chloride in solution for the first case, which is 23 weight percent water. And you can see that at the so-called pure water dew point, the temperature starts to increase, but it never quite increases enough to precipitate ammonium chloride solid. In contrast, the lower concentration does indeed precipitate ammonium chloride solid at about 200 Celsius, as shown in the chart on the left. Again, if you have a model for these systems, one can use it as a virtual laboratory to provide calculations that are of interest to practicing engineers. And I really wanted to emphasize these points in the conclusion to the second case study. One is small concentrations of acids and bases can significantly elevate the water dew point. And it is important for us as practicing engineers to quantitatively understand this effect to mitigate two problems: corrosion and fouling. With that, Sabrina, I think that concludes the second case study, and we can go and see whether we have any questions from the chat.
Thanks, Paul. Yes, we do have a couple of questions from the chat. So the first one is, how are electrolyte systems modeled?
Okay, that's a good question, because that comes into case for sulfuric acid as well as the next one, which is ammonium chloride. We've been modeling electrolytes with process simulators going back, I would say, 50 years. An early pioneer in this business was a company called OLI Systems, which is based in New Jersey. My co-author, whom I talked about, Professor Chao Chen Shan, actually for his doctoral thesis at MIT, came up with the electrolyte NRTL model, which is in Aspen Plus, and we use this. There are probably two aspects. Electrolytes, of course, are very complicated, but let me leave you with two important aspects. One is when you get electrolytes, they're ionic, they have long range forces, so the activity coefficients become complicated. More importantly, though, we need to figure out the dissociation constants. In the sulfuric acid example, we could have some molecular sulfuric acid in the system and also molecular water in addition to the ions. And the second example, we could have ammonium chloride in the system, which could precipitate as a solid. So all of these chemical equilibrium are very, very important. It's a complicated system, but I'm confident that we have good ability to model these systems. That's not to say that we are done. We still have lots of research projects that are ongoing around the world to improve our ability, and we should also always try to do better. Going back to data, though, the one I emphasized before, I think the data is very important, and I think if we have data, that goes a long way to describing these systems. So that's the answer to that question. Thank you.
Okay. Another question, do you have an idea of how accurate thermodynamic models are to predict water dropout in CO2-rich mixtures? And how much uncertainty or margin should be considered?
Water dropout in CO2-rich mixtures. In general, I don't think that's a problem. We have our CO2 capture processes, and we do have water washes. It's not necessarily a big problem because we do that quite well. There is some association there, but I think related to that, if you take CO2, the bigger problem I think is washing the solvent out. And that helps actually because the solvent is one that dissociates, and therefore the water and the CO2 will help drop it out so that we actually do not send any of the solvent into the environment. If there's more on that, maybe I can rethink it through the chat and send a better response or a more detailed response to the attendees at the webinar.
Okay. Well, keeping an eye on our time, we will move on to our third and final case study.
Okay, let me move to the third study. This actually is a simpler system, and because I brought it up because I think it actually highlights the need for us to carefully validate and verify our models. So let me get into this example. This came to me about 4 years ago, and I got a call from a process engineer. He was simulating a methanol refining column and was getting an ethanol impurity in the methanol product, which comes out as the distillate here, of 25 mole percent, and this would be a mole percent by volume as opposed to the previous one I talked about, whereas the licensor said that it should be 5 mole percent. Now this is a relatively simple system. Essentially what we are separating it's a water methanol system, and the ethanol has a very good relative volatility with methanol, and we should be modeling it correctly. But as I started to go into it, I realized that the details mattered. And in fact, this is a case where we needed to be really accurate and verify our correlations carefully. So let me go into some of the details in the next slide, and maybe in the Q&A I can answer any questions you may have. I want to point out that I published a paper on this subject just last year, so the viewers may go to this publication for details. But let me give you the key details. The curve on the left here shows the liquid mole fraction of ethanol as a function of height of the column or number of trays. I just want to point out that number 1 corresponds to the top. So the left is the top, and the bottom, tray 33, is the bottom, and the feed tray is tray 29. So you can see that in the top section, the two correlations work quite reasonably. They didn't make much difference. Here I'm talking about the correlation in the original correlation that came from the vendor in the commercial simulator, in this case AspenTech, and the one that we developed, which I'll talk about in a minute. But as you get to the bottom of the column, you see that's where we see the difference between 9 ppm and 25 ppm. In order to understand that difference, you go to the curve on the right, which shows the activity coefficient of ethanol. And you can see here that the AspenTech correlation gives an activity coefficient of 1.08. The correlation we came up with gives an activity coefficient of 1.02. Both are actually pretty close to ideal, and the difference between the two is only about 6%, but it does make the difference. So the question is, what is the correct answer? So to do that, we need to go back to careful evaluation of data, which I will talk about in the next few slides. Let's talk about the importance of the procedures and practices that we need to focus on in order to develop a reliable and accurate correlation. So let me talk about the ones that I consider important. One is, it's very important to have careful data analysis, and the best way to do this is trend plots. Plot the data and look at it, compare, and see what it is. We human beings are actually very good at spotting trends. So I would encourage everybody to make trend plots and evaluate them. You will see problems right away. The second one, and you probably learned this in your thermodynamics course, is it's important to fit different kinds of data. In this case, it's important to fit the vapor-liquid equilibrium as well as the excess enthalpy data. And finally, again, a different twist on trend plots is family plots, and that is properties within the family should have certain trends. And I've published on this, and I can send you some details if you like. I also want to point out that I am a co-author of the latest edition of Perry's, and we did put some of these patterns into, I believe it's section 4 on thermodynamics. Let me then move on to a discussion of details. This plot shows the methanol-ethanol relative volatility, which you probably know is the ratio of the K values. And this is as a function of the ethanol liquid mole fraction, and the system is at 1 atmosphere. So you can see that relative volatility is actually reasonably high, but the question is, how accurate should it be? The green line shows our correlation, and you can see that it agrees quite nicely with the data we considered to be most accurate, which is KERO 1993. It is also quite good agreement with the data we call ARC 1998. Data on details on these data sets are in our paper. But through analysis, we concluded that the other two data sets are not accurate, and we actually did not include them in our data fitting. We also included some excess enthalpy, and I won't show you details here, but we did do that. So we concluded that our green line is accurate. The dashed lines here show 1% difference, and the dotted lines show 10% difference. And our analysis is that our correlation is probably good to 1 or 2% for ethanol, methanol. And you can see that that made all the difference in the previous slide, which modeled the distillation column. We move on to one more example here, and that is, I want to point out that if you do use commercial simulators, the correlations could be really bad if you don't evaluate them. Here's one that came from the infinite dilution of isobutanol in methanol, and you can see the temperature dependence. There's something clearly wrong with it. Possibly data was fit over too small a temperature range with too much temperature dependence of the parameters. But the point is that this correlation could give very poor results. Now, if you did plot them, you would look at it and say, well, this doesn't make any sense. So that's an advantage of a trend plot. Let me move on to a family plot. And this one is going to show you the infinite dilution activity coefficients of several lower alcohols in methanol. Again, the details are in the paper. Again, you can see that this plot kind of makes sense. One would expect isobutanol to be the most non-ideal in methanol, and those activity coefficients go something of the order of greater than 1.4 to 1.3. Butanol is slightly less non-ideal. Propanol is even more non-ideal. And as you remember, I told you that the activity coefficient of ethanol in methanol is something of the order of 1.02. So the trend plot, the family plot starts to make sense, except if we look at isopropanol. So what is going on here? When I started to get this trend, I went into the literature, and it turns out, like in most things, thermodynamics, somebody else had studied it. And there's a gentleman by the name of Dr. Benson, who worked out of Ottawa, Canada, who took a lot of very accurate heater mixing data in the late 60s and early 70s. And through his data, he came out to the conclusion that isopropanol, which is a secondary alcohol, has a favorable interaction with primary alcohols, which would be ethanol, methanol, ethanol, and propanol. And that's the reason why the activity coefficients are actually less than unity. There's another subtle detail here, and that is if you look at the activity coefficient of isopropanol, it has a positive slope, and the other ones have a negative slope. And again, if you go back to your thermodynamics, that comes from the heater mixing. If the heater mixing is positive, greater than unity, the slope is negative. And if the heater mixing is negative, the slope is positive. So thermodynamics is actually quite powerful. And all these relationships that you probably sweated over and hated when you took the thermodynamics course are indeed important for process technology. Let me take a slight detour here and give you a next example that actually came from a different source. My colleague in the next office, or at least the next office before COVID-19 hit us, is Henry Kester. Henry Kester is a very distinguished distillation expert, and he has been providing this course, practical distillation, for more than 20 years, and it's taught throughout the world. When I showed him my paper, he said, "Oh, you know, I've actually been presenting a slide like this for a long time in my distillation course, and this slide was contributed by a major chemical company." Let me quickly go over the slide. We don't have that much time. So what the slide says that if you have a reviewed correlation, we can say that the confidence level is good. And hopefully the correlation I showed you for the low alcohols would be in this category. And as you go down this list here, though, the confidence level decreases. If it's not quite so much reviewed, maybe it's 80%. If it's a commercial simulator, it's possibly 40%, and that's what I found too. In sort of defense of the commercial simulators, I've got to say though, they're providing correlations without knowing where they will be used. And of course, so that's a very hard way to provide the correlation. On the other hand, we as practicing engineers know where it should be used, and therefore we should be doing a validation. As we move down the list here, you can see that UNIFAC, which is a group contribution method, performs worse. And possibly, if you're very lazy and say that some pairs are ideal, you could be down in the 0 confidence limit. So let me then quickly go in and give you the lessons learned. One is, the message I want to leave with you is correlations from process simulators need to be checked. Actually, we do have pretty good tools to develop correlations. We have databases. I mentioned the Dipper database before. That applies to pure components. In addition, we have the NIST TDE, which I've used a lot because it's available in Aspen Plus, and also the Decima database that comes from Germany. and is one of the best databases in the world. I've used that one too. So data is indeed available. Secondly, is that software to regress model parameters is easily available. If you know what data you can pick to regress, yeah, it's very easy to do the data regression. The point I want to leave you with, though, is correlations need to be checked for trends as well as family plots. And lastly, and I believe that this is what Henry advises people in his course to, please be skeptical. If you are using correlations, be skeptical, because all correlations do need to be verified. I then would like to get to the conclusion after I've given you 3 case studies for this webinar. One is that thermodynamics is indeed an established tool for process design and operation. But I also wanted to make the point that it's good for ensuring safe plant operation. And in my estimation, this is an underappreciated value, so I wanted to emphasize it. And lastly, I want to re-emphasize and emphasize again the point I've made several times, is that the results depend entirely on the validity and the accuracy of the correlations. So practicing engineers should verify. If you remember what Ronald Reagan, president, said, trust but verify. So that's the last message I'd like to leave you with, and I think we have some time for questions, and I hope you've sent some over the chat. Thank you.
Thanks, Paul. Yes, we've had a very engaged audience, and they have been submitting quite a few questions. So our first question is, how does Fluor use thermodynamic knowledge in its CO2 capture technology?
Okay, I did publish a paper on this subject at a 2013 conference or 2014 conference on thermodynamics. In fact, one of the examples that we presented there was how thermodynamics helped us sort out the heat of solution. We went back, and in fact, one of our collaborators on that was Professor John O'Connell, who was my thesis advisor. And at that time, he was a professor at the University of Virginia. So we went back in and reevaluated the Gibbs-Helmholtz equation and came up with how we could estimate the heat of solution. And at that time, people were claiming a very, very low heat of solution for aqueous ammonia. And we proved that to be incorrect. And in fact, that was verified by experimental data that came later. But as far as Fluor works on this is an area that's very important to us because it's one of our core technologies. We've developed a very good thermodynamic model using some of the procedures and practices that I've talked about here. In addition, we've gone in and tried to verify the kinetics and the mass transfer. One thing I should mention is that this is another example of electrolytes because these are chemical solvents and they are weak bases. So as soon as they interact with CO2, they form ions in solution. So again, the electrolytes knowledge becomes important. The last thing that we have done is actually go to pilot plant data. We've gone to small scale pilot plants and indeed also ran a pilot plant in Wilhelmshaven, Germany for a few years. So we've put a lot of work into it. It's too much detail to go through here, but I'll be happy to answer any questions that come over the chat.
All right, Paul, we have about 5 minutes left before we're at the top of the hour. And so I still have a number of questions for you. Isn't there also dimerization of methanol in the vapor phase, hence the Hayden-O'Connor model?
Yes, the answer to that is yes, but that our application was at 1 atmosphere, and so that effect was small. We did evaluate that, and it didn't matter. Now, if you're running it at higher pressures, yes, indeed, we should be worrying about vapor phase dimerization, and the Hayden-O'Connor model actually is a very good model and a standard one that needs to be used. There are actually lots of twists in here. The alcohols in the liquid phase indeed have some very strong interactions among themselves. And so that may need to be taken into account. And in particular, if you mix alcohols like methanol together with hydrocarbons, you could have very, very strong activity coefficients different than unity. So I think one of the keys is to pay attention to the individual system you're working with and apply the model that makes the most practice sense. And also compare with data. We should be comparing with data all the time. As we are learning from the current pandemic we have, data is king.
Very true. Another question. How do you identify the accuracy of data set? It says it's always hard to sort out which data is useful and which is not.
Well, that's actually a difficult question. You know, most recently we are doing this a lot better. One of the jobs I have other than Fluor is an associate editor at the Journal of Chemical Engineering Data. And for the past 10 years at least, we've had a collaboration with NIST, where as the last review of papers, we asked them to provide uncertainties, and actually these are reviewed by NIST. If you go back to data from about 20, 30 years ago, there's no uncertainties provided. But more recently, we are paying much more attention to this aspect. It's a learning curve, but I think as a whole thermodynamics community, we've gotten much better at uncertainties, and hopefully that trend will continue. Because as we've realized, data is no good if we don't have the so-called metadata, which tells you how uncertain it is.
Paul, another question. How many people at Fluor have a similar skill set to yours? Since we're losing the skill set in many operating companies.
That's the elephant in the room question. When I started off at Air Products in the early 80s, we had 6 people doing thermodynamics. But now as I look at companies, it's dropped off considerably, so that expertise has dropped off. And the feeling is, oh, we can rely on the commercial simulators. But as I pointed out here, no, we cannot. We really have to verify. So I think it's sad that the expertise is going away, and I myself am not a young person. I think it's for the next generation to figure out how we're going to deal with this problem. And hopefully remember that this is an important skill that does not come from pushing buttons, but rather takes some expertise.
Well, thank you, Paul. So being mindful of the time, we will close questions for now, but Paul will respond to the remaining questions via email. So Paul, thank you for your insightful presentation. I think we've got a lot of people here who are very engaged, and we're very grateful for you sharing your knowledge with us. And thank you to our audience for joining us today. We really appreciate your attendance this morning, this afternoon, or this evening, depending on where you are. On Thursday, August 6th, we will host our next webinar with Fluor Senior Fellow Rick Drake and Senior Design Engineer Jennifer Memmott, where they will discuss additions to existing structures. So please keep in touch with your Fluor contacts and follow our social media postings so that way we can invite you to future webinars. If you have any questions or require additional information, please email innovation.builders@fluor.com and our team will get back to you. Thank you for joining us and have a safe day.